It is my great pleasure to give a talk at the very beginning of this META conference. Okay, today I'm going to talk about integrated nanophotonics for optoelectric computations. So this is the tight outline of my talk today. And first, I will give a brief survey of the optical computing and introduce some example of the optoelectronic computings. And then I will show our recent studies of three key issues for optoelectronic computations: OE and EO conversion, and nonlinear functionalities, and also linear optic functionalities. And finally, if I have time, I will briefly show some more functionality based on topological nanophotonics. Okay, so as you might know, the optical computing was extensively studied in 80s and 90s, but it turned out that it could not compete with CMOS processors. Then, in terms of computation, optics was being used as an optical interconnect in 2000. However, this trend is recently changing. In fact, a number of novel optical computing methods or technologies were proposed and demonstrated recently. And I understand that there are at least 4 reasons for the revival of optical computation. First, in contrast to the 90s, the performance and latency of CMOS processors are now being saturated. So they look for other technologies. So that is one reason. Second, there is an increasing demand for the computation power, especially for the analog computation, because of machine learning applications. Third, there has been substantial progress of integrated nanophotonics. Large-scale photonic integration becomes possible, and footprint and consumption energy were greatly reduced. And also the large-scale interference circuits becomes possible. So those did not exist in 90s, 80s, and 90s. Fourth, optoelectric computation becomes feasible because photonics and electronics convergence has been progressed very rapidly. Furthermore, as I will show you later, the energy and the latency cost of OE and EO conversion has been greatly reduced. So this shows recent trend of CMOS processors, showing that the integration density is still increasing, but the performance and the latency are already saturated. And we are expecting that the cyber world and physical world will be connected in the CPS society. And for the real-time CPS societies, the latency will be a bottleneck. So the next I will introduce optoelectronic computing. So this illustrates a typical optoelectronic computer or optoelectric accelerators. And this accelerator is tightly connected to the CMOS processors. And it takes charge of computation requiring small latency with small energy cost in this computer system. The optoelectric accelerator is consisting of 3 parts. The first part is a linear optic electro-optic gate, EO gate circuit. And this linear optic circuit is set by electronic signal, and the calculation is done by light propagation from here to there, and at the speed of light. And in many cases, this circuit utilizes light interference. The second part is here. It's a nonlinear element. In many situations, we need some nonlinearity. The last part is OE and EO conversion. And this part is very important because any optical computing core should be somehow connected to electronic circuits equipped with a large memory. But in many cases, the optical circuit does analog computation, and therefore digital to analog conversion is also important, required. So here I show this, the first example of optoelectric accelerators, which is a parallel full adder. And usually this kind of ripple carry adder consists of AND, XOR, and OR gates. But these functionality can be represented by just two Mahat-Sender interferometer, MZI, here and there, with one EO modulators. So just 3 gates are sufficient for representing these operations. An important point is that this carry transportation, this is a critical path for this computation. And this path is all optical. So this means that this carry transportation is done at the light speed. So we fabricated this full adder circuit for 5 digits using silicon photonic platform. Like this, there are the 5 digits circuit. And this is a critical path. And this is a photo of the fabricated chip. And this slide shows the experimental demonstrations. And this result, left-hand side result, is showing the all possible, actually it's 128 combinations of 4-bit addition operations. So we confirmed it gave a correct answer for all cases. And in addition, this shows the repetitive operation at 100 megabit per second and even more here. And here I show another example of optoelectronic computation, which is a neural network. As you know, the neural network consists of vector matrix multiplication and activation for multidimensional vectors. And it is widely recognized that this VMM is most energy and time consuming process in deep learning. And in fact, this VMM can be done by light propagation. And as shown here, a certain type of MZA matrix circuit can perform unitary matrix operations. This was proposed by Leck in many years ago. And this can function as a VMM. Actually, the Shen et al. At MIT, they proposed and demonstrated this idea in 2017. And this shows our recent experimental work using a similar universal unitary matrix circuit and by MZIs. Here we employ a so-called Clemens type unitary circuit. So the structure is a little bit different. And we confirm that it can perform inference operation for simple classification problems. So here we confirmed an iris classification. It's classified as 3 types. And in this case, we use the reduced MNIST classification. We only use 5 numbers out of 10, but they perform quite well. So, okay, so far I showed that the light speed calculation is possible by the certain types of optoelectronic computation circuits. And as I told you, there are 3 parts consisting of optoelectronic accelerator generally. So hereafter, we show our recent advance concerning these 3 parts. And the first is OE and EO conversion. And the key point is we use ultra small capacitance nanophotonics. And OE and EO conversions are considered as the most power-hungry process for optoelectronic integrations. And the energy of OE conversion is mainly determined by the transimpedance amplifier after the photodetectors, and which consumes several hundred femtojoule per bit. And the energy of EO conversion is determined by the charging energy of EO modulators, which is typically 10 to 100 femtojoule per bit. And these values actually limit the performance of OE optoelectronic accelerators. In fact, these energies are limited by the capacitance. And this shows a typical capacitance comparison of photonics and electronic devices. The capacitance of conventional OE-EO converter, OE-EO conversion devices are 1 or 2 orders of magnitude larger than that of CMOS transistors. And actually, this is a fundamental reason why OE-EO conversion are so power hungry. However, recently, we achieved a sub-femtofarad capacitance for OE and EO conversion devices using photonic crystals. Here I show our work for the OE conversion devices, namely the photonic crystal photodetectors. And this photonic crystal photodetector has an extremely small capacitance of 0.6 femtofarad. And in spite of such a small size, this photodetector shows high performance comparable to the high-end photodetector used for the optical fiber communications. It's a high sensitivity and low dark current and high speed. And also an important point is that because this capacitance is so small, we can add the high load resistance to the photodetector, and we can generate the large voltage without use of transimpedance amplifier and without sacrificing the operation speed. And importantly, the rise to voltage conversion efficiency is 4 kilovolt per watt, which is even better than that of conventional photodetector with a transimpedance amplifier. Moreover, this photodetector shows very low noise because it does not have TIA, and it does not suffer from the thermal noise. In addition, this photodetector can operate even at the forward bias conditions. Although normally the photodetector is used as a backward negative bias conditions. And it can operate even at the 20 gigabit per second. So this means that this photodetector can function without a bias voltage if it is equipped with a high load resistance. So actually, this is something like a solar cell, but operates at a very fast speed. So therefore, this small capacitance photodetector will lead to ultimate OE conversion. Since it does not have an electronic amplifier or bias circuits, so it does not require any electric energy. And also the footprint is very, very small and low noise. So this OE converter will perform very good in the optoelectric accelerators. Next, I show you our recent work for EO conversion, namely an EO modulator. Here again, we achieved extremely small capacitance of 0.6 femtofarad because of this photonic crystal design. And it can operate at 40 gigabit per second. And the most important point is that the consumption energy is as small as 42 attojoule per bit. And this value is actually 1 or 2 orders of magnitude smaller than that of previous EO modulators. This is primarily due to the small capacitance. Okay, so I showed that the small capacitance nanophotonics dramatically change the energy cost of OE conversion and also the EO conversions. So, which is very important for considering optoelectronic computations. Okay, so next I will talk about nonlinear functionalities. Here, we combine ultra-small capacitance photodetector and ultra-small capacitance EO modulator through a load resistors here. So when optical pulse is injected to this photodetector, the resultant photocurrent is converted to voltage across this resistor. And this voltage drives EO modulators. Therefore, so this CW input is finally modulated. So in fact, this is an OEO converter. Well, in other words, this is 3-terminal photonic devices, something like an optical transistor. And this shows the frequency response of this OEO device. This proves that the total capacitance of this integrated device is just a 2 femtofarad. As far as we know, this is the first femtofarad level optoelectronic integrations. And this shows a PD response without electric amplifiers. So it can generate the large amount of voltage, and this voltage can drive the next EO modulators. So this shows EO modulator response. So, so this can function as a optical transistors. And importantly, this OEO device shows a signal gain, shown here. It is, and also it shows very high speed nonlinear operations with substantially small optical energies. So as a total, this OEO device can function as a very efficient optical nonlinear element with signal gain. Actually, this is what we require for optoelectric accelerator. For example, this OEO device can be used as an activation function in optical neural network. So I just showed hybrid type OEO nonlinearity. But here I want to show you the all-optical nonlinearity. And this shows a comparison of energy versus time for various optical nonlinear gates. Also, most of the conventional nonlinear devices are located above this line. We achieved all-optical switching at sub-femtojoule regime by using photonic crystal nanocavities almost 10 years ago. However, this region, a picosecond or sub-picosecond regime, has been still difficult to achieve. Actually, this is limited by the photon and carrier lifetime of this photonic crystal nanocavity system. So to achieve this region, we looked for a different material, graphene. As you know, the graphene is a very efficient broadband absorber with a very large absorption coefficient. And it shows ultra-fast optical nonlinearity, namely such level absorption. And at the 100 femtosecond to a few picosecond level. So hence the graphene is a promising nonlinear, optical nonlinear material, ultra-fast and the energy efficient and broadband. However, graphene's performance is limited by its small interaction cross-section because it's so thin. So we investigated graphene with deep sub-wavelength MIM plasmonic waveguides shown here, which enables the ultra-strong light confinement. And as a result of strong light confinement, the device size becomes reduced in comparison to the graphene on a silicon waveguide. And the graphene's absorbance is also increased. And most importantly, the field intensity at graphene is greatly increased. This is very important for the nonlinear operations. So encouraged by these numerical estimations, we fabricated graphene loaded MIM waveguides. And this core size is 20 nanometer by 30 nanometer. So this in the deep subwavelength regime. And the important point is that we employ a very efficient plasmonic mode converter. It's SEM photography shown here. And this shows the comparison of existing plasmonic mode converter. Actually, we regard that the mode converter is one of the most important elements for plasmonic device applications. And this comparison shows that our converter shows a very good coupling efficiency, even at the deep subwavelength core size. So we performed the experimental demonstration of all-optical nonlinear gate operation by using pump probe method. The resultant switching window is 260 femtosecond, and the pump energy is as small as 35 femtojoule. So we achieved sub-picosecond nonlinear gate operations. In fact, we successfully achieved sub-picosecond operation with substantially small energies. So this is a comparison of the previous record, and our device, graphene plasmonic device, is located here. Now, as far as we know, this is a record low energy for any sub-picosecond switching operations. So therefore, we think this graphene plasmonics hybrid system may be important ingredient for ultra-fast all-optical nonlinearities. Next, we move on to linear optic functionalities. And here we focus on the use of the optical interference. Recently, we proposed this kind of simple 3-to-1 silicon waveguide combiner device, which we call the Psygate. And in this device, the interference between A and B is controlled by this bias input. So as shown in this table, this same device can perform the various different Boolean functions by just changing the power or phase of bias input. So we can use it as XOR or AND or blah, blah, blah with the same device. And this shows the experimental demonstration of multiple Boolean operations, AND, XNOR, and NOR for the same device. And another important feature is that this device operation does not depend on the wavelengths because it's just an interference device. So it doesn't have a strong light wavelength dependence. So this is experimental data. And since Psygate is a purely linear optic device, so this result indicates that we can perform different operations for different input data simultaneously when each data is coded at different wavelengths. So namely, so we can do the WDM computations. So of course, the device operation speed is very fast because it relies on just the interference. And this shows experimental demonstration of 40 gigabit per second operations. And in addition, we can integrate Psi gate. This is one example. So this shows integrated AND gates for multiple inputs. And recently, we proposed to apply the similar optical interference to realize digital to analog converter. Here, an electric digital signal is converted to an optical analog signal by use of interference. Importantly, the latency of this EO-DA converter is much shorter than that of electronic DA converter. So this is what exactly required in optoelectric neural network accelerators. And interestingly, the total loss of this DA converter decreases when the bit number increases, which is just opposite to previous optical DA converter proposed. And very recently, we fabricated 4 to 8-bit EO DA converter and demonstrated DA converter operations. As far as we know, this is the first optical DA converter operation for multiple bits. So that this summarizes various device technologies I explained today within the optoelectric accelerators. We believe that the combination of these technologies would lead to optoelectric accelerator with ultra low latency and small consumption. Okay, so within the rest of my time, I will briefly touch on our another research direction. And we are currently interested in looking for novel degree of freedom in photonic processing, such as photonic topological properties. And especially interested in reconfigurable topological photonics. So I show just a few slides for this last topic. As one example of reconfigurable topological photonics, we designed the photonic crystal loaded with phase change materials, GST. And the point is this GST is patterned in some particular way. And when GST is at the crystal phase, so this photonic crystal has a trivial photonic band gap. And when GST is at the amorphous phase, so it has a topological band gap. And thus it has two edge modes. So this is one example. And as another example, we investigate a tunable nanocavity array in which we can independently control the gain and loss for each cavity. So this is actually the reconfigurable non-Hermitian one-dimensional periodic system. And we found out that this periodic system can show topological band gap when we introduce 4-cavity unit modulation of gain and loss in this way. And this shows a band gap, topological band gap. And thus it has an interference edge mode. And important point is so in this structure, the cavity array is equidistant. So that's this topological phase is created only by gain and loss controls. So this means that we can create the interface edge modes anywhere by controlling the injection current. So concerning this experiment, so recently we demonstrated this simple 2-cavity system for this photonic crystal nanocavity for the current injected platform. So before concluding my talk, I show our research member for this present work. And I acknowledge these members in NTT and Tokyo Tech and IST, Nagoya University, and Kyushu University. So this is a summary of my talk today. I showed 2 examples of optoelectronic accelerators for other and neural network. Then I presented our recent studies for 3 key technologies, OE and EO conversion by using ultra small capacitance, and the nonlinear functionalities by using OEO converter and also the graphene plasmonic system. And the linear optic element by playing with the optical interference. And I showed some brief report for the reconfigurable topological photonics. So this concludes my talk, and thank you for your kind attention.
Thank you, Masaya, for this series of state-of-the-art results. I would say that keep us dreaming on optical computing. I was already in the field in the 80s and 90s, you know, so always a little bit skeptic, you know, because of course I agree that optics is making considerable progress. Optoelectronic, let's say, electronics also is making progress. Let me look. I mean, I don't think that we have questions. No, but I encourage people to, let's say, use the button in Zoom to ask for questions so that the chairman can repeat the question. I'd like to talk about, let's say, fundamental limitation. Of course, you have shown, I mean, record results, and that's very impressive for the OE conversion or for the switch with something, if I remember, whether you are below the femtojoule, but is there some kind of fundamental limitation? Because I agree that, let's say, transport is an advantage for optics, but any nonlinearity is really a penalty. So according to the architecture that you are looking, there should be a balanced result, even for neural networks that were looked at 20 or 30 years ago. So do you see some fundamental limitations on, can we increase the performance of the switching, for instance, which is very important, I guess, which is a...
Okay, so let's say the switching case, I don't think the current performance is fundamentally limited. So for example, if we can reduce the size of cavity more, then we can still decrease the energy. So of course, the fundamental limitation will be a single photon, and there is no fundamental limitation to achieve such a single photon situation. But the more serious problem is if we only use the optical nonlinearity. In that case, normally the signal gain is difficult to achieve. So I think this is very fundamental limitation by using the optical nonlinearities. So that's why we would like to use the combination with the electronic some functionality. I mean the OEO conversion. In that case, is the total functionality is all optical, but inside there's optical and electric conversions. So that involvement of the electronic transition, that is a very important key for achieving the signal gain. So I'm not sure that this could be your answer to your question, but I think all optical computers has a certain limitations. So we need to combine with the electronics in some clever way.
Yeah. Okay. Thank you. You need to balance. I mean, I think you need to have much more interconnection than nonlinearities. Is it correct? Simply, is it the balance is simply there?
But for doing so, we need to reduce the capacitance, because capacitance is a key for combining the electronics and photonics.
Yeah, but then I was thinking the area which is occupied by a photon is lambda square. And so the capacitance associated to lambda square in a CMOS circuit should be much larger than the capacitance of a CMOS transistor, for instance. Is it correct? Is it a simple way to think about, or
I don't
I missed
think
something?
so. I don't think so. It's because, for example, our case, the capacitance is, I would say it's almost comparable to the capacitance of CMOS gate. So if we simply compare the wavelengths of electrons and photons, there are probably 2 or 3 orders of magnitude difference. But for the capacitance, there is no such a big gap. Because the capacitance is determined by the configuration of the 2 electric plates. So there is more freedom for making the size smaller.
So the cap, okay. Take some question maybe from the audience. Sorry about that. So we have questions. I mean, yeah, there is a question from Cristiano Matricardi. Which are the greatest challenges we have to face to bring topological photonics out of the lab?
Yeah, that is actually a difficult question. And to be honest, I don't have clear image for application for the topological photonics, but we are expecting there could appear some new novel functionalities. So actually I work for an NTT, and also I work for the university, Tokyo Tech, and the topological photonics is mainly done at the university. So it is, I think it's still there's some distance for the applications. And for example, I think that the topological photonics is very suitable for playing with the degree of the polarizations. So we can make use of the polarization degree of freedom more complicated way by using topological photonics. But anyway, I don't have a clear image. Sorry.
Yeah, we have also a series of other questions that I will not ask. I apologize for that, but you also received many congratulations for your talks in the question. So I am going to, let's say, to close this session, and thank you again for this dreaming. I mean, it's dreaming always talk on, let's say, optical computing. And thank you all the audience for